Welcome to the e-lecture session for diploma students. In today's session, we are going to deal with the various parts of the transformer, and one such topic is the construction of Buchholz relay. Already we have started with the parts of transformers in the previous session. In continuation of that, we are going to deal with the construction of Buchholz relay. It is a relay which is mainly connected in the pipeline between the main tank and the conservator, designed in the form of a vessel filled with oil which is dome in shape. The device can be easily subdivided into two portions inside the vessel depending on its purpose and also its structure, that is the upper part and the lower part. Upper part. The upper part contains a float which is directly connected to a hinge, and a mercury switch is just kept over the float. On the other side, the mercury switch is kept in such a way that the terminals of the switch, when made to contact with the alarm circuit's terminal, it makes a closed circuit. Thus, the float is made to move up and down in the oil immersed vessel, so that the terminals of the mercury switch gets connected and closing the alarm circuit for making us alert at the time of some internal faults. So, the actual purpose of this upper part is to alarm us about the faults. Then comes the lower part of the Buchholz relay. The lower part of the Buchholz relay is concerned with the detection of serious or major faults, and thus completes the trip circuit to open the circuit breaker operating the transformer. It contains a hinged type flap on which another mercury switch is kept. The mercury switch on the other side is placed in such a way that with the movement of the flap, the terminals of the switch will connect with the terminals of the trip circuit. The flap plate is placed in just between the flow path of the oil and gas between the main tank pipe mouth and the conservator pipe mouth. Working principle of Buchholz relay. The main working principle of Buchholz relay depends upon the generation of hydrogen gas inside the transformer oil tank. When the transformer oil is subjected to a considerable amount of heat, then it gets decomposed and produces hydrogen gas H2. Generally, an alarm circuit and a trip circuit are connected with the relay mechanism. The tripping procedure of both the coils, and hence the working principle of Buchholz relay, is described as follows. Working of alarm circuit. The main reason of attaching an alarm circuitry is to alert the working personnel about the fault. If any fault occurs inside the transformer, then a huge amount of heat will be developed. So, this critical amount of heat will decompose some part of transformer oil from the main oil tank. This decomposition of oil generates a considerable amount of hydrogen gas inside the tank. We know that the hydrogen gas is lighter than the oil. As the conservator is situated at the top position of a transformer, so after generation the entire amount of gas tends to reach the conservator tank by flowing in the upward direction. But as the Buchholz relay is located at the pipeline, so when flowing to the conservator, some amount of gas is also entrapped by the upper portion of Buchholz relay. More amount of heat leads to generate more amount of hydrogen gas, and thus more gas will be accumulated inside the relay chamber. When the amount of gas tends to approach a predetermined safety value, it creates a pressure to the float which leads to tilt the float. After the movement of the float, the upper mercury switch will get closed and create a complete circuit for the alarm. So, this is the schematic diagram of Buchholz relay. I will zoom this on. You can see here. So, this is to alarm, this is the float, and this is the mercury switch, hinged point, and to trip circuit. This is to trip circuit. Whenever this mercury switch is closed, right, this will issue signal to the trip circuit to trip it. So, this is from main tank, this is to the passage to the conservator. So, this is the test cock which can be removed to refill the oil, so to filter the oil, etc. So, this is the flap which holds the trip circuit arrangement. Now, let us move on to the working of trip circuit. When a serious fault occurs, then heat will be produced inside the main tank. So, a huge amount of oil is decomposed, and this leads to generate hydrogen gas. The inrush of gas is much higher in that case, and when rushing upward to the conservator tank via the Buchholz relay, then a considerable amount of gas gets trapped into the relay and immediately tilts the flap arrangement. After the movement of flap, the mercury switch is automatically closed and provides a closed contact for the trip circuit. Now, let us move on to the tap changer arrangement. In case of power system networks, the voltage supplied by the transformers can be varied by changing its transformation ratio. This can be achieved by tappings which are provided on the transformers. The tappings are the leads which are connected to various points on a transformer winding. These terminals are brought outside to permit access to the windings. Thus, the number of turns present in the circuit with one tap are not same for another tap. The turns ratio is therefore different with different tappings, and hence different voltages are obtained with different tappings. Now, you can see here, I will zoom this picture on, you can see more clearly. So, you can see here. So, once you connect this common with once this 1 and common are connected to the input supply, then the actual rating, the transformer will work on the actual rating. Suppose if it is 1 kVA, then it will the rating will remain as 1 kVA. Suppose if I want to change this, I can connect the supply to 2 or 3 or 4. So, by changing this, you can vary the number of turns associated with the primary. Accordingly, once you connect the supply voltage to 4 and common, then the number of turns associated with the primary will be minimum. Similarly, once you connect the supply to terminal 1 and common, then the number of turns associated with the primary is maximum. So, there are 4 tappings. So, the voltage associated with the primary can be changed by changing the tappings. So, this is the LV side which has no tapping in this configuration. The tappings are placed either on high voltage or low voltage, or sometimes on both high and low voltage windings. The figure 4.36 shows the transformer with the tappings provided on high voltage winding. when a transformer is required to give a constant load voltage despite changes in load current or supply voltage, the turns ratio of the transformer must be altered. This is the function of a tap changer. Types of tap changer: one is off load tap changer, the other one is on load tap changer. Off load tap changer: in this method of tap changing, the tappings are changed when the transformer is disconnected from the supply. As per the requirement, the tappings are taken out on the respective winding and the connections are brought out near the top of the transformer. Manually operated selector switches are provided for change in tappings. The commonly used switches are vertical tapping switches and faceplate switches. The off-load tap changer is shown in the figure 4.37. Let me zoom this on. You can see here. So, these are the selector switches through which the selector switches the tappings can be selected 1, 3, 5, then 1, 4, 6 and all. The above arrangement is normally used to get plus or minus 5% change in steps of plus or minus 2.5%. It consists of an insulating base on which 6 brass or copper terminals are mounted. The contactor is mounted on an arm of the shaft. The central or middle part of the winding contains the taps and the taps are connected to terminals of the tap changer. The shaft can be rotated from one position to another so that the selector switch is connected to adjacent pairs of stationary terminals. Then on load tap changer. On load tap changers, as the name suggests, permit tap changing and hence the voltage regulation with the transformer on load. Tap changing is usually done on the high voltage winding for two reasons. So, this is on load tap changer. Here there are two selector switches 1 and 2, then this is the diverter switch. Because the currents are lower, the tap changer contacts, leads etc. can be smaller. As the high voltage winding is wound outside the low voltage winding, it is easier to get the tapping connections out to the tap changer. This is because already we have seen this in the construction of transformers. So, this is the primary and this is the secondary. So, if this is the core, normally the low voltage coils will be wound first, on top of it after the insulation the high voltage coils will be wound. So, since all the tappings are taken from HV, that is high voltage winding, it is easy for the access of all the tappings. That is what it states. As the HV winding is wound outside the LV winding, so very near to the core the LV winding will be present. Upon construction of the LV winding in the limb of the core, then comes your high voltage winding. So, as the high voltage winding is wound outside the LV winding, that is low voltage winding, it is easier to get the tapping connections out to the tap changer. Figure 4.38 shows the connections for an on load tap changer that operates on the HV winding of the transformer. Now, The selector switches 1 and 2 are provided on taps 1 and 2 respectively. The diverter switch is connecting tap 1 to the neutral terminal of the transformer winding. Then comes the transformer oil tester. The dielectric breakdown strength of the transformer oil is one of the most reliable tests for ascertaining the condition of the transformer oil. So, this particular transformer oil test kit is employed to find out the strength, that is the dielectric breakdown strength of the transformer oil. The BDV test should be conducted when the sample is cold and not the hot oil gives a higher BDV, thus misleading the investigation. In the testing equipment, there is a test cup. This has 2 electrodes in the form of spheres. One is 13 mm in diameter. The sphere gap should be exactly 4 mm by the side of the test cup. By the side of the test cup, screws have been provided and we can adjust the gap suitably by using the screws. Also, there is a step up transformer here. The test electrodes are connected across the secondary terminals as shown in the figure 4.39. Let me zoom this on. You can see here. So, this is the auto transformer variac. So, this is the primary and this is the secondary. Here is the test cup where the electrodes are placed. So, by varying the auto transformer sliding contact, you can vary the magnitude of the input voltage applied to the primary. Now, the primary winding of the transformer is supplied through a variac. By operating this variac, we can gradually increase the test voltage as required. It has been so arranged that the contact S will be closed only when the variac output is 0 volts. The test cup is filled with sample of oil. The level of the oil should be at least 1 centimeter above the level of the electrodes. The cup is then covered with a clean glass plate and allowed to rest for 5 minutes, so that any air bubble that may be present inside will disappear. When the on button is momentarily pressed, the coil M is energized. Main contact M1 then closes, thereby connecting the output of the variac to the primary winding of the step up transformer. Then the contact S is in closed condition as the variac is in minimum output position. The sealing contact M2 then closes. Now, the no load current has no effect on the coil B to open the normally closed contact B. The test voltage is now increased uniformly at a rate of 1 kilovolt per second of the specified value. The voltmeter connected is calibrated to show the high voltage side voltage. A good sample of oil withstands 22 kilovolt for 1 minute. So, the variac is again adjusted so that the voltage increases from 22 to 33 kilovolt. When breakdown occurs in the oil across the electrodes, there is corresponding surge in the primary winding and the coil B immediately opens. Now, the coil M is de-energized and the contact M1 opens, disconnecting the primary from the output of the variac. The breakdown voltage is that voltage at which sustained arcing takes place. The reading of the voltmeter should be noted at the time of breakdown. Then acidity of transformer oil. Acidity in a transformer oil is objectionable as it leads to corrosion on the metal parts of the transformer immersed in the oil. Oxygen may be present inside the transformer due to air remaining in oil, air pockets trapped in the windings, etc. The oxygen reacts with the transformer oil and oxidizes it. Such oxidation produces organic acids and sludge. Metals, particularly copper, encourages the oxidation process of oil without undergoing any chemical change in itself. The operating temperature of the transformer rises due to this chemical reaction. Therefore, the transformer oil should be checked for acidity once in a year in the case of power transformer and once in 2 years in the case of distribution transformer. The prescribed limits for acidity are as follows. When the acidity is less than 0.2 mg bar KOH bar grams, the oil is in good condition and the corresponding neutralization number is equal to 0.02. Number 2, if the neutralization index is between 0.02 and 0.05, sorry 0.2 and 0.5, no action needs to be taken if the oil is satisfactory in all the other aspects. Number 3, if the neutralization index is between 0.5 and 1, the oil should be kept under observation and filtered if necessary. And finally, point number 4, when the index exceeds 1, then the oil should be removed and purified. So, this process has to be done once in a year for a power transformer and once in 2 years in the case of distribution transformer. Then comes the acidity test. The acidity index is determined by using the portable acidity testing kit. The kit contains the following. Number 1, 2 polythene bottles containing 100 ml each of ethyl alcohol and sodium carbonate solution. Number 2, an indicator bottle containing universal indicator as supplied by the BDH division of Glaxo Laboratories. Number 3, 4 clean glass test tubes. Number 4, 3 graduated droppers, 1.1 ml 1 number and 1 ml 2 numbers. And finally, fifth one, color chart calibrated with neutralization numbers. Now, let us move on to the testing procedure of the transformer oil. 1.1 ml of the transformer oil to be tested is accurately pipetted into a clean and dry test tube. 1 ml of ethyl alcohol is added with this and the mixture is gently shaken. After an interval of about 1 minute, 1 ml of sodium carbonate solution is added. After shaking the test tube again, 5 drops of the universal indicator are added. The resulting mixture develops a color From this color, the acidity can be determined by comparing with the standard chart supplied with the kit as given below. So, this is a chart. So, color observed and the neutralization number in mgm bar KOH bar gm. If the color is orange, then the neutralization number is 1. If it is yellowish orange, the neutralization number is 0.8. If it is yellow, then the neutralization number is 0.6. For greenish yellow, neutralization number is 0.4. Olive green, it is 0.3. Parrot green, it is 0.2. Then ultramarine, it is 0.1. When it is Prussian blue, it is 0.05. And finally, if the color observed is indigo, then the neutralization number is 0.00. So, up to 0.2. So, when the color is indigo or Prussian blue, then ultramarine, up to parrot green. So, the condition of the transformer oil is considered to be good. You cannot afford to change it at this point. From 0.2 to 0.5, then you have to consider. From 0.5 to 1 onwards, the other conditions apply. Then we will come to the important topic called as earthing. Earthing means direct electrical connection of all metallic non-current carrying parts of electrical equipment such as metal frame, motor body, etc. to earth. Earthing can be classified as number 1 system earthing, number 2 equipment earthing. Earthing of neutral in powerhouses and substations belongs to the first category. The purpose of system earthing is to protect the equipments in the system from lightning, earth fault, etc. Earthing of non-current carrying metal parts of electrical equipment is known as equipment earthing. Example: transformer tank, then motor frame. Equipment earthing ensures safety. If there is accidental contact between a live conductor and the frame due to failure of insulation between them, no fault current will flow. If the frame is not earthed, the equipment will continue to function normally. If somebody touches the frame of the equipment with bare foot, they will get shock. But if the frame of the equipment is earthed properly, the voltage of that parts with respect to earth does not rise to dangerously higher value. Thus, severe shock is prevented. Earth fault can operate fuse or circuit breaker because of sufficient earth fault current. A thick strip of copper should connect the frame to the ground, and the earth electrode should offer minimum resistance to the current flow. Now, let us move on to the methods of earthing. One is direct earthing system. In this system, the parts of an installation to be earthed are connected directly to the ground. Thus, the system neutral can be grounded effectively or non-effectively. In effectively grounded system, the neutral is grounded directly and hence it is called solid grounding. Number 2, multiple earthed neutral system. In this system, the parts of an insulation to be earthed are connected to ground, as is the case of direct earthing system, but these parts are also connected to a neutral conductor of the supply system. Number 3, earth leakage circuit breaker system. In this system, the parts of an insulation which have to be protected are connected to an earth electrode through the coil of an earth leakage circuit breaker. It protects the insulation by disconnecting the faulty circuit. Then we will move on to the very important topic of measurement of earth resistance. So, here is the arrangement for the measurement of earth resistance, which is called as earth tester. So, there are 3 electrodes available here. One is the earth electrode, then potential electrode, and the current electrode, which is represented as B. Potential electrode is represented as C, and the earth electrode is represented as A. Earth resistance can be measured directly by earth resistance tester. It essentially consists of a hand driven DC generator, a rectifier, metering system, etc. The DC voltage generated is converted into AC and then applied to earth in order to avoid electrolytic action. The current coil is energized by the earth current. The pressure coil gets energized by the voltage drop caused by the earth current. These two coils form an ohmmeter. The earth tester also works nearly on the same principle of a megger. The earth resistance of the electrode A can be measured directly with the help of an earth tester. C and B are two auxiliary electrodes of 15 to 20 millimeter diameter and 40 centimeter long bars. The electrode B is planted at a distance of approximately 25 meters from A, and C is fixed centrally between A and B. The handle of the generator is rotated at normal speed and the meter reading is noted. Two more readings are taken by shifting C at a distance of 3 meters on either side of its central position. The instrument should indicate nearly constant readings in these 3 positions. If it does not, then B should be moved away from A by approximately 6 meters and the experiment must be repeated till constant readings are obtained. This value is the resistance of the electrode A to earth. So, before concluding this session on the various tests of transformer, we will have a quick recap of whatever we have learnt in this session. So, we have started this session with the various parts of transformers, Buchholz relay, then tappings, the importance of tappings on the high voltage side, then we have seen something about the transformer oil test and acidity test, and then finally we ended up with earthing. Thank you.